Question 7.33. Draw all of the expected products for each of the following solvolysis reactions. So a solvolysis reaction, in 7.33b, we have a tertiary alkyl halide, and we have water, which is a weak base, and it's also a weak nucleophile. So this is why it's going to undergo solvolysis. So what's going to happen in the first step, and it's not asking us to draw the mechanism, but we're going to get that loss of leaving group, and we're going to form the tertiary carbocation. I think it's handy to help us, it's handy to draw that out. So we understand that if it undergoes an SN1 mechanism, that the water is going to act as a nucleophile, and then I'm going to have a proton transfer, and I'm going to end up with a tertiary alcohol. So I'm going to skip drawing the mechanism, and I'm just going to draw the product. So in this case, we would end up with this molecule, which is an achiral compound. So this is the SN1 reaction. And then if the water behaves as a base, so we could put here SN1, we could put water as being a nucleophile in this case. And if the water behaves as a base, well, there's two types of beta protons in the molecule. I have these three beta protons in this methyl group, and then I have the two methylenes. So if I eliminate the proton that I have highlighted in blue, I would end up with this alkene, and then I have also these protons on the two CH2s or methylenes. So that would also give me this compound, so this alkene. So in terms of these two alkenes, this one would be the major of the alkenes because it is more substituted. It's the Zaitsev product. So if I take a look at the next example, so I have a tertiary alkyl halide, and what's interesting in this case, I'll just draw the carbocationic intermediate after the loss of leaving group. So if I draw, here's my phenyl, I draw 1, 2, 3 carbons. When I lose that leaving group, what I end up with is an sp2 hybridized carbocation. So now this is trigonal planar, and I don't have to worry about this stereochemistry. And then what's going to happen is, if my methanol, so this represents methanol or methyl alcohol, when it reacts via the SN1 mechanism, and first the methanol will attack the carbocation, then I get a proton transfer. The methanol can attack from either side of that trigonal planar sp2 hybridized carbon. So I'm going to end up with a mixture of enantiomers in this case. So we'll draw both of the enantiomers. So I'm going to get this compound, so 1, 2, 3, and then I'm going to have my wedge coming out here. So I'm going to end up with this ether, and then I'm going to abbreviate the benzene or the phenyl as pH. I'll get that enantiomer, and then I will also get, not a lot of room here, I'll get this enantiomer. Then in terms of elimination, so you can see that there's a couple of types of beta protons that I could pull off. Here you can see that there are these beta protons here, that'll give me an alkene, and then there's these ones as well. So if I pull up the one that's on the top, I would end up with this product. So I'd end up with this alkene. But in terms of removing this proton, I can get a Z alkene and I can get an E alkene. So I'll write them down here. So I'll get this one like this. So this would be the E alkene, and then I will also get the Z alkene. So if I put this like this, so this is the Z alkene. So this one is going to be the major between the E and the Z because it's less sterically hindered and it's the most substituted. So it's the Zaitsev product. So I hope you find this helpful for question 7.33.